Hey everybody, this is the second problem that I gave out on Friday for the open-ended. This is a little more abstract because we're going to be using no real numbers in this solution. So again, I'm assuming you already read it. So we know that Lily's walking around this at a constant velocity. That's the easy part. Tulip is a little more difficult because she changes her motion as time goes on. So in order to analyze this, what I'm going to do is I'm going to create a velocity versus time graph. This is usually your to-go graph in order to analyze something effectively. So I'm just going to create a graph right here on the side. And I'm going to say, all right, the velocity over time. And over time. Okay, so it says that Tulip walks around the track where she starts off with a velocity v and then speeds up to a velocity of 2v by the time she reaches halfway down. So halfway down, she reaches her maximum velocity and then slows back down after a side is done. So if you're thinking about it this way, right around, if she's starting right here, she starts right there. As she's walking, she's speeding up, and then after this part is reached, she starts slowing down. Here, she's at a velocity initial again, or v again. This is v. Right here, she has 2v. And then over here, in the middle, right around here, this is 2v, because she's speeding up here, and then slowing down at the lower half. Now here again, she starts off with v. By the time she gets up the middle here, she's speeding up here, and then slowing down here. So, and over here she has a velocity of 2v. So her graph is going to look a little strange. So just labeling her graph, label this v. I'm going to label this over here 2v. Okay, and so making this graph, I know that I'm actually going to extend this line across. This is just going to be a reference marker, guys. Okay. Sometime t1. Now, for the first part of this motion, I realize that since she's speeding up halfway through, that half the time here, she's going to be moving quickly. Now, if that's t1, then I'm also going to say that this is going to be 2 times t1, right? Where this has the same duration as this guy over here. Because these two sides, well, they're the same length. If she starts on this particular end of the triangle, if she starts here, then the time it takes her to walk this path and then down this path are going to be the same. She has the same kind of motion. So continuing that idea, we're going to get the same kind of shape in the second half or second portion of her motion. Now, I'm going to say that this down here is going to take maybe longer. I don't know how much longer. And it's going to be, I don't know, some other time, t2. So this length is going to be different, some t2 length. I don't know what it is, but it's going to have kind of the same shape, but just like kind of stretched out because it's a larger motion. So halfway through. Now, here's the thing. We need to figure out which person completes one loop around the park in the fastest time. So we need to compare the times that Tulip walks around and the time that Lily walks around. Lily is kind of easy because she's moving at a constant velocity. If we want to figure out how long it takes, we know she walks a total of 4d. So that's her total distance walked. And she travels that amount of distance by traveling at 3v divided by 2. So that's like 3 v divided by 2. And if you multiply 3v divided by 2 by how many seconds, or how much time she decided to walk, well, then you have an expression of this, which is how far somebody moved, this, which is their velocity, and this, which is how long they took to move. This is very similar to delta x equals v initial t plus 1/2 at squared. Well, you might be saying, well, where's the 1/2 at squared? Well, Lily is walking at a constant velocity, so that disappears. So you're only left with this portion, which is reflected in the equation above. Solving that equation above for Lily just gets me 8d divided by 3v equals t. So this is the time for Lily. That's how long she takes to walk around. Well, let's compare this time, the time that it takes Tulip to walk around. Now, let's see. I need to find the area of these graphs, because finding the area will allow me to easily express how far she moved and how long. So I'm just going to divide up these portions right along here. And I'm actually going to copy this, create another line around here. So then we have these areas of motion where we can actually find, using just these letters, how much area is in between these points, right? Okay, so I seem to be doing that a lot. All right, now for this, for the blue highlighted area, each one of these areas are the same because they're just identical. It's the same length of path and the same type of motion. So finding out the area is just as simple as doing, well, the base of this is like t1. The height of this is just v. So really this is v t1. The area of this guy is the base of the triangle, which is t1, times the height of the triangle, which is actually another v. It's very simple. So it's 1/2 v t1. So if I'm finding the total area of both things, I can say, oh, well, I know that the area of this entire shape right here, is going to be 1/2 v t1 plus v t1. That's the area. That's what you did in the previous problem. You just used numbers instead of letters. This total, you can combine them to be 3/2 t1. Oh, vt1. So this simplifies to 3/2 v t1. And that's actually how far that person moved during this time. So, well, we also know that that's equal to the length of that first part of the path. That's equal to d, actually. So looking at this expression, you're like, oh man, that's really similar to the expression over here. I can just solve for t and figure out how long it took for this first part of motion that I've highlighted. So that's easy. Finding how long t1 is equal to, if I solve, 2/3 d divided by v. Okay, now that's just for this first green part that I highlighted right here. Well, it's actually the same for this part because, again, they're identical. So I know that the first and second parts, well, this takes time t1, and this also takes time t1. Okay, so now I know that the time that Tulip takes is going to be equal to t1 for the first part of motion, which is in green right over here, plus another t1 for that second part because they're identical. So that this portion just turns into 2t1. And then the last portion, I need to find the area of that too. That's kind of easy. This portion down here is the base, which is some amount of time t2 times v. So v times t2 and 1/2 v times t2 on the top. The total of this ends up being 3/2 v t2 equals 2d, because this path down here is 2d long. So that's how far Tulip moves during this time. So solving for t2, well, easy. t2 is equal to 4/3 d divided by v. Now I can take that and I know, oh, so the first two parts of motion was t1 and another t1. And the third part of motion, I just got to tack on this t2 over here. Well, okay, so knowing all of this, I know that her Tulip's total time, I'm going to put it down here, Tulip's total time is equal to 2t1 plus t2. All right. Well, I can plug in for those t1s and t2s because I solved for them. t1 is equal to 2/3 d divided by v. So I can say, all right, well, it's 2 times 2/3 d divided by v plus t2. Oh, 4/3. Sweet. So 4/3 d divided by v. You can combine all this stuff together. 2 times 2 ends up being 4/3 d over v. So 4/3 d over v. Oops, d over v, sorry. Plus 4/3 d over v. That ends up being 8/3 d over v. So Tulip takes a time of 8/3 d over v. Lily takes 8/3 d over v. They take the same amount of time. Nobody is fastest in this problem. And that's how you do this problem.